So there's going to be times where you have to take more derivatives after the first, and we will see this when we get into our next chapter on applications of derivative, and also we're going to get into sketching curves, and we're going to see that we can use derivatives to help us sketch functions. Yes. Okay, and so that's going to have a couple uses when we get into sketching certain graphs. Okay, so since the derivative of a function f is also a function, the second derivative f double prime can be found. The second derivative can also be denoted by f double prime or f double prime at x or d squared y over dx squared. So they all mean the second derivative. And so this first example asks us to find the second derivative of each of the following. So the first one, you're giving y in terms of x. The first derivative will be dy by dx, which will be 6x to the fifth. And then the second derivative, d squared y over dx squared, is found by just repeating the process using the power rule. So 30x to the fourth would be the second derivative. For question 2, I would probably multiply out those two binomials first. That gives us 2x squared, then minus 4x plus 3x is minus 1x minus 6. Sorry, that's not f prime x, that's still f at x. And now we can find f prime x, which will be 4x minus 1. And f double prime x then will just be the constant 4. You don't have to, but then you'd have to use the product rule to differentiate. This is much easier. Yep, it would work. So in this case here, you can't go further. You couldn't take the third, fourth, fifth derivative because now we're down to a constant. But for the first one, you could. Question number 3, like we've done before, we start by making sure that every term is written as a power. So root x is x to the half. And then we will differentiate. The first derivative would be 10x plus 1/2 x to the negative a half. And then our second derivative will be 10. And then when you use the power rule for that last term, the negative a half exponent is multiplied by the positive a half coefficient. Will give you negative 1/4 x to the negative 3/2. Or 10 minus 1/4 x to the positive 3/2. And you could get a common denominator there of 4x to the power 3/2. Notice no brackets here because the x only applies to the 3/2 only applies to the x, not the 4. This first term would have to multiply by 4x to the power 3/2 because its denominator is currently 1. So that'll give us 40x to the 3/2 on top, take away 1. And you could do one more step if you wanted to. You could rationalize the denominator by multiplying top and bottom by the square root of x cubed, because that's what x to the 3/2 means. Okay? You also, I guess, in this case, could multiply top and bottom by x to the negative a half, because when you multiply x to the 3/2 times x to the negative a half, you would add the exponents, you'd get x to the 2 halves, which is x to the 1, or just x. Then you'd have a negative exponent on that second term on top, so you'd want to deal with that as well. So there's a few things that you could see happen in order to take that further. Right, for question 4, we'd have to use implicit differentiation to differentiate that second term, but the derivative of the first term would be 3x squared plus, so that'll be 3y squared dy by dx. Remember we did this yesterday, equals 0. Then you solve for dy by dx by subtracting.
Oh, yeah.
Because remember, this is 5x to the power 0. That's what that really means. So you'll subtract the 3x squared from both sides. It'll become a negative over on the right, and then you would divide by the 3y squared, which is what's in front of dy by dx. So that'll give us negative x squared over y squared as our first derivative, simplified. But now for the second derivative, d squared y over dx squared, we're going to have to use the quotient law here because you've got negative x squared over y squared. So we'll use the quotient law here. Derivative of the top will be negative 2x times the bottom, which is y squared, minus the derivative of the bottom will be 2y dy by dx times the top, which is negative x squared, all over the bottom squared. So that'll become y to the 4th. So right now, we want to find the second derivative. That's what we're trying to get. So you need to simplify what d squared y over dx squared is. We need to simplify what's on that right side. Okay? So there's a couple of things we can do here. First, that second term on top, we can multiply everything out to simplify that a little bit. So it'll be a negative 2y times a negative x squared, which will be positive 2x squared y dy by dx all over y to the 4th. But we need to do something with that dy by dx there. Because remember, one of the applications of derivatives, the one we've been using mostly so far, is to find the slope of the tangent. So that would be from the first derivative, which you could do, but then we're also going to see there's going to be practical uses of taking the second derivative. We're going to see a couple different things that the second derivative can be used for. So if we wanted to do that here, we'd have to do something to get rid of that dy by dx. However, up top, we do have an expression for dy by dx. dy by dx, we found, is equal to negative x squared over y. So we can take that expression and substitute it down there. dy by dx is negative x squared over y squared. So we'll make that substitution. So we have negative 2xy squared plus 2x squared y times dy by dx, which we found to be negative x squared over y squared, all over y to the 4th. So now we'll simplify to get our final answer. So it's going to be a positive 2x squared times a negative x squared. That'll give us negative 2x to the 4th. And you've got this factor of y on top. You've got y squared on the bottom. So that'll become 1 over y, or y to the negative 1. All over y to the 4th. And once again, there are a few things that we can do here to simplify this further. So here we go. First thing is that y to the negative 1 on top could be written as a denominator. We've got negative 2xy squared minus 2x to the 4th over y, and that's all over y to the 4th. So we've done this before where we've got a denominator in the numerator, and we got rid of that by multiplying all the terms by that common denominator, in this case by the letter y. So that first term will become negative 2xy cubed minus 2x to the 4th all over y to the 5th. What we can do next is on top, there is a common factor there of negative 2x that we could take out, which will leave us with y cubed plus x cubed as our second factor. And that y cubed plus x cubed we can simplify because at the very start we are told that x cubed plus y cubed is equal to 5. That's our original expression. X cubed plus y cubed equals 5, so we can replace that y cubed plus x cubed by 5. And we'll get negative 10x all over y to the 5th. So a couple substitutions that we did there to simplify this expression. There is. So in this case, we want to find the 5th derivative. So if f of x equals the original expression, the first derivative would be 4x cubed plus 6x squared minus 10x plus 3. Our second derivative, 12x squared plus 12x minus 10. Our third derivative would be 24x plus 12. Our fourth derivative will be 24, and then our fifth derivative will be 0. Because the derivative of a constant is 0. We're not going to see any applications past the second derivative. We'll use the second derivative for a couple different things. But in this course, there are no applications for any derivatives after the second. Pardon me? It could be part of this chapter. So those are the questions that you're going to work on. But first, we're going to go through your limits exam.